Okay, review video number 6 is all about impulse and momentum. So if we start out with the basics of momentum, okay, momentum is a lowercase p, so don't forget about that, and that's equal to mass times velocity. So because it does have velocity involved, which is a vector, momentum itself is a vector as well. And there's no special units here, right? Our units of mass are kilograms, and our units of velocity are simply meters per second. So those are our units for momentum. Now, this can be something as simple as, a person with a mass of 40 kilograms is running at a velocity of 10 meters per second. Okay, what's the momentum of that person? Well, then you would do the mass times velocity. Okay, plug in everything you know, 40 kilograms, 10 meters per second, and they would give them a momentum of 400 kilograms meters per second. And then you may have to include a direction if it gives you direction in the question, such as east or west, whatever. In this case, my direction would just be to the right. If it asks for a magnitude, though, remember magnitude is only this part. Okay? You do not need the direction if it asks for just the magnitude. More often, though, we're going to be using, the change in momentum equals mass times change in velocity. All right? So it might be a car with a mass of 1,000 kilograms. It starts from rest and ends up traveling at 5 meters per second. Okay, so if it's starting from rest, well, first of all, its mass is 1,000 kilograms. And if it's starting from rest, then its change in velocity is final minus initial, so it'll be 5 meters per second. That's what it ends up at, minus the initial, which is 0. So its change in velocity is just simply 5 meters per second. Okay, and that would come out to be 5,000 kilograms meters per second. Nice and easy. Now, where things get a little bit trickier is with conservation of momentum. Okay, and conservation of momentum comes into play with any sort of interaction. It can be an explosion, it can be a collision, and typically the collisions are what we're talking about. But there's two types of collisions. There's elastic, okay, and inelastic. Elastic is where they don't stick together, and inelastic, they do stick together. Now, this is going to give us, different ways to do this equation for conservation of momentum. And the basics of conservation of momentum is that the momentum before equals the momentum after. Okay? So, let's say we have two carts held together by a spring and then a string on top of that. Actually, let's get rid of that string. Let's just go with the spring. Okay, and we have this cart has a mass of 3 kilograms. This cart has a mass of 1 kilogram. And so right now, because they're held together by that spring, okay, it's a compressed spring and they're at rest right now, the momentum before is 0. Okay, now if we cut that spring and it releases them, and then we can say that this cart ends up going off with a speed of 2 meters per second. We want to know how fast this one is traveling. Okay. So the momentum after is just the total momentum. So it would be the mass of the first cart times its velocity plus the mass of the second cart times its velocity. But that would be equal to 0 because that is our momentum before. Okay? So really what it comes down to is m1 v1 equals negative m2 v2. All right? So we can say that the mass of cart 1 is 1 kilogram. We're looking for that velocity. Then we have negative 3 kilograms times 2 meters per second. So if you do the math here, our velocity, v1, comes out to be negative 6 meters per second. Okay? That means it's traveling 6 meters per second. The negative means it's going in the opposite direction. So that's the basics of conservation of momentum if we're starting from rest. Okay? Now, if we look at, let's say, an elastic collision. Oops. So in an elastic collision, this is where they don't stick together. So we could have, call this cart A, has a mass of 2 kilograms, initially at rest. Okay, and here comes cart B with a mass of, let's give this one 4 kilograms, and it has a velocity of, let's say, 3 meters per second. Okay. Now they're going to collide, but they're not going to stick together. And after they collide, let's say this would be the before. Let's say that after cart B is traveling at 1 meter per second, and we want to know how fast cart A is traveling. Okay, and we might not even know a direction. They might not give it to us. And this would be the after scenario. So we start out with momentum before, equals the momentum after. So that's the mass of cart A times its velocity plus the mass of cart B times its velocity equals the after scenario. They're both moving, so that would be the mass of cart A again times its final velocity, which you use a little tick mark for, plus the mass of cart B times its final velocity. So initially, let me go back and just check real quick. Initially, we've got a 4 kilogram mass going at 3 meters per second. Cart B is at rest, so that would just be 0. And finally, we have that same 4 kilogram cart going at 1 meter per second. And we want to know how fast that, was it 2 kilograms? Yes, 2 kilogram cart is traveling. So we're looking for that final velocity. So here we have 12 kilograms meters per second equals 4 kilograms meters per second plus 2 kilograms times our final velocity. So we bring that 4 kilograms over to the other side. We have 8 kilograms meters per second equals 2 kilograms times the final velocity. And we solve for that final velocity to be 4 meters per second. Okay. Now what you do have to be careful of is negatives. Okay. If it said that, cart B was traveling backwards at 1 meter per second, then we'd have to make sure that we make that a negative, in which case it would add 4 kilograms meters per second to the 12, and that would give us a different final velocity for B. So just remember, anything that's going in the opposite direction is negative, anything going in the same direction is positive. Now, inelastic, they stick together. So our initial, or momentum before, is still the same. Okay, that M1 V1 plus M2 V2, or A, B, whatever they are. But now, after they collide, they stick together. So they're moving as one unit, which means they're going to have the same final velocity. And the masses are now stuck together, so we simply add the masses together. We can solve for that final velocity. It's very important just to remember to watch out for direction on that. Okay, I'm not going to go through and do a sample one for this one just because we're running low on time. Now, impulse, okay, signified by a J, is equal to force times time which is then equal to the change in momentum. Okay, and the units for this one can be a Newton second, which is a unit of force times a unit of time, or it can also be a kilogram meter per second. They both mean the same thing. Right? So now what this is that when you apply a force to an object over a certain amount of time, it's going to change the momentum of that object. So applying a force over an amount of time changes that momentum. Now, if we're talking about two objects interacting, so a good example, let's stick with a golf club hitting a golf ball. Okay, we saw that in class. So when the golf club hits the golf ball, the golf club is applying a force to the ball, but the ball is applying a force back to the golf club as well. And Newton's third law tells us that that force from the club is equal to the force from the ball. And they're in contact for the same amount of time. Okay, you can't have one in contact with the other for a longer period of time, so the times are the same. That being said, that the impulses then must be the same, they're just in opposite directions. So the impulse from the club on the ball is equal in magnitude to the impulse from the ball on the club, but just in opposite directions. And then because of that, they're both going to change momentum. So the ball is going to increase its momentum because its velocity is going to speed up. The golf club will decrease its momentum because its velocity is going to slow down. Now they're both going to increase or decrease by the same magnitude of momentum because each of these would be equal to the change in momentum. All right. Now obviously the masses of the golf club is different than the mass of the golf ball, so their momentums are going to, or I should say their velocities are going to be different because the masses are different, but their total change in momentum is going to be equal, but again, opposite. The golf ball is going to pick up momentum, it's going to increase in momentum. The golf club is going to decrease in momentum. Now, last thing for impulse here. Very rarely, but sometimes they do give you a question about a force time graph. Okay? And they might give you something like this. And they'll ask you, what's the impulse from this force time graph? Since impulse is force times time, okay, and we multiply these two together, it's simply just the area under this curve. Okay, area under the curve of a force time graph gives us the impulse. If you have any other questions about these, don't hesitate to ask.